The next speaker is also a very dear friend of this conference. FLEXOPTIX have been involved with DKNOG for many, many years now, and we're very grateful for their assistance. And I think it's quite appropriate that we continue a little bit in the optical domain, because I'm pretty sure there's somebody here who's not as much as a router jockey, but maybe more into that optical domain. And certainly this one wins the prize for longest conference item title. And quite a lot of acronyms here. So I hope that you're all excited for some more optical stuff. Just buying time here. It's analyzing network reliability up to 800 gigabit, the G is for gigabit, impact of SNR, that's signal to noise ratio, thresholds on BER, bit error rates, yeah, for coherent, 16 quadrature amplitude modulation, and non-coherent PAM4, oh now I'm lost, high-speed transceivers under environmental variations. I think you're ready now. Take it away.
I have to stay here. First of all, thank you very much, Ellen, for the introduction. So this is great, thank you. But I take the analog version with the keyboard. Hi, my name is Thomas Weible, CTO and co-founder at FLEXOPTIX, and this is Gerhard, our lead research engineer at FLEXOPTIX. And we have a new topic today about 100 gig. Ellen already did a perfect introduction, so there's nothing I have to add more. We did some research, especially what we can tweak out of transceivers, and that's what we're gonna show you today. So, first of all, that's a little bit the agenda for now, for the next 25 minutes. We're gonna do a small recap from last year from DKNOG, where we did a talk about coherent transceivers. And then we jump straight into the bit error rate dependencies, look a little bit on testing devices, and then our outcomes on especially temperature. That's a critical thing when we talk about bit error rate testing, and the distance of the fiber itself. And then finally, we have some takeaway, and yeah, Gerhard gets his setup as well. So first of all, recap from last year. A little bit about the theory part we discussed last time about SNR and BER, so signal to noise ratio. It's pretty straightforward. So it's our desired signal is the peak in the middle, and we have the noise level at the bottom, and we want to achieve a lot of margin between the desired signal and the noise level, because otherwise the receiver, it's really hard for the receiver to distinguish our desired signal. And in combination with that, the bit error rate also correlates with the SNR. So when the SNR gets worse, also typically your bit error rate gets worse. That's in a nutshell. Now we jump a little bit further back in the history, about 6 years ago, when we first introduced the setup of the latest QSFP-DD development about transceiver technology, what is inside of a QSFP-DD or OSFP module, and in these days also in QSFP28 100 gig modules, there is this tiny bug in there, the digital signal processor. And we showed the digital signal processor has capabilities to do forward error correction. We don't want to talk today about a forward error correction much, but we want to look at the bit error rate capabilities, the BER tester, and also the OSNR, or in general the SNR, which are all functions of the DSP inside of every single 400 gig transceiver you're using these days typically, and even 800 gig, or in some circumstances when you operate single lambda 100 gig, also you have the DSP inside. So how did our lab setup look like? Pretty simple. We, in parallel, we developed the latest generation of Flexbox 5. You see it here on the screen. It's really tiny. We had also some power issues, but that's a different story. And here you see an 800 gig transceiver. It's a DR, a QSFP-DD 800 on a DR8 with the fan out. solution, and we opened up the housing because we had some heat issues. What did we test? A couple of transceivers. We started with 100 gig, single lambdas, different distances. Went on with 400 gig, even included coherent modules, and then also looked at the latest one, the 400 gig QSFP 112, and also at the 800 gig QSFP DR8. And with that, I hand over to Gerhard.
All right, thank you very much. Se me escucha? See, you can hear me, all right. Yeah, what are the ingredients you have to buy if you want to do these tests? As Thomas already mentioned, distance or fiber length is interesting. We are building up a loop, and temperature, because our assumption is that these are the factors that have an influence on the bit error rate. So when you check our job, you can buy one of these drums. And I'm putting here the attenuation per kilometer. Why is this important? Because we wanted to get up to 60 kilometers. But if you want to drive a transceiver that can work with fiber of 60 kilometers, you should check specifications. And we were particularly interested in out of region, out of bound setup. So I took a 40 kilometer one and tested with a 60 kilometer fiber, and I went down to 2 meters basically to see the differences. If you do that, you have to be careful, because there's one challenge, and now I extend my list of ingredients. You have to attenuate it properly, because if you connect a 2 meter fiber to a transceiver that is specified for 40 kilometers, you might damage the photodiode. That is a thing you don't want to do. But on the other hand, it makes us a little bit difficult to compare it, because on longer fibers you remove the attenuation, on shorter fibers you have to add it. So it is possible to compare. That is what I did in this case. And yeah, I mean, you can look up into the shop if you decide to buy a transceiver and you want to use it on different lengths, or I mean, you know your setup. Yeah, please look forward to this. You can look up what the limits are. So what do you see here basically? We have the different length from 2 meters to 50 kilometers. The 60, we didn't get any signal anymore, which was to be expected on a transceiver that is specified for 40 kilometers. But still, you can run it with 50 kilometers. And what is interesting, this red section you see, is the specification for IEEE 802.3, which says a bit error rate of 2.4 times 10 power of -4 is still tolerable. This is prefect. So that is a bit error rate you can measure from these transceivers. Since they have a DSP, you can really measure it on the transceiver and say, okay, I'm looking at the media side, what raw data rate I can get. The transceiver does this for me, thanks to the DSP that is inside. So I started with 11 dB attenuation in total, compared the first 3 different fibers from 2 meter to 20 kilometer. But when I jump to 30 kilometer, I have to remove attenuation, because I'm really out of the tolerable bit error rate. It was going into the red section. So in order to change that, I removed some attenuation, and as you can see, the 30 kilometer curve drops, and that is the effect you observe if you don't damage your photodiode. Now, one thing more interesting about this is, yeah, the temperature changes, especially with the 2 meter variant, but with more kilometers, it's not that much. Now you see these red circles, interestingly. What happened there? Well, basically these transceivers and its DSP have a firmware installed, and what this firmware does, the software inside of it, is using a lookup table. So if it sees that the temperature goes higher, it tries to control. It has like sort of a control circuit, you could say. It changes current, it changes voltage, and basically that is the result you end up seeing. So the bit error rate improves the higher the temperature goes for some temperature at a certain point, but after that it got worse again. So yeah, it's not the message that you should not cool it down. Getting to bit error rate, easy formula, I'd say. but there's certain complexity if you want to measure it. And one value I want to give you as a takeaway here is the gating time. The gating time tells you how long do you have to wait until you see your first error. Unfortunately, it is not that easy. You usually use 100 samples, so you assume that I'm measuring 100 errors. Why is that? The reason is because you have some statistical noise, some Gaussian noise, and with that you better assume 100 errors, and with that you can be sure that at least one of these 100 errors is a real value that is really erroneous. So that is what you usually do, and with that you can calculate your gate time. And here you see with an example of 100 gigabit per second and bit error rate that we are assuming to a power of -12. It takes about 16 minutes. But if you assume that your bit error rate is way worse, so this assuming we have the prefect IEEE standard, you would get it after 4 microseconds. You will see up to 100 errors. So bit error rate in that sense is very important to measure and to keep it as down as possible. Yeah, right, yep. Thomas. And
so then we moved on, and instead doing the test with direct detection transceivers, we used the coherent modules. And so we had to open up the Flexbox anyway, because, yes, I already mentioned we had some heat issues, especially to get rid of the heat. So we were able to feed in all the power, but yeah, it got really hot. So this was our entire lab setup, and the interesting part, or the funny part actually, is about this heat sink. So we grabbed that from an old Cisco 800. A good friend of mine, he's a wrecker. He disassembles quite a lot of equipment and around Frankfurt area in Germany. And he recycles basically everything. And so if you need support getting rid of your equipment in Frankfurt, let me know. He does a proper job. He does it really great. So we got the heat sinks from him, and yeah, moved on with our next tests on the coherent one.
Very good heat sinks, and thank you very much. Exactly. In this diagram, it looks a little bit similar. Maybe the curves smoother. What's the difference? As Thomas mentioned already, this is a coherent transceiver. I have to mention low power one, because here it looks like I'm not using any attenuators. That's the case with this coherent transceiver. You can do this. You can run 2-meter fibers and 60-kilometer fibers, and you get values. And now you see you have a higher bit error rate. That's a specification of a different agreement. The OIF agreement says that the value of prefect typically is in between 1.5 and 1.3. -4 and -2, so that's the range where it moves usually. We are within this range, as you can see, with all these different measurements, so we are fine on that side. But what is quite interesting is, yeah, there's an influence on length, chromatic dispersion, not impedance. We have different effects with optical light you're transferring. But the temperature doesn't have such a big influence. So that is what we have observed with coherent. And I think it's not so hard to explain. The coherent has a pretty high resolution on a more complex system. What is happening and recovering and demodulating basically that complex signal we have. Like in our previous talk, you might remember this diagram he explained. Our coherent transceivers have the 16 QAM diagram, so like 16 dots, so 16 times the different data you have in one packet. You have a better resolution, and I guess it's not so temperature sensitive, as we can observe here. Basically, we tried the same without cooling. So yeah, I mean the bit error rate increases. As you can see, we didn't show the 60 kilometers anymore because this was really out of this diagram. It really failed with the signal. So there you can see there's still an influence. You still should cool it because it can recover the signal, but after a certain point, if you surpass that range, the transceiver starts notification with loss of signal. So do not get any signal. And what usually happens is your bit error rate, it shows either 0, which is unrealistic, or 1. So these two values, you don't want to see them. If you start running your transceiver and you see it in the beginning and it recovers and goes down, that is okay, or goes up from 0. But if it stays at these exact values, exactly 1 or exactly 0, that's a wrong signal. It's basically a loss of signal. So right, one of the more interesting experiments we tried out was to get the transceiver hot. Why? Because we want to tell you what happens if a fan of your network gear fails. You might know that transceivers don't do the control circuit. Some of the firmwares might try to shut down the transceiver, but usually the transceiver is a device that sacrifices himself or herself, itself, basically. So it is really the responsibility of the network gear to decide what to do if the temperature raises. And since also the network gear is in charge of cooling down the transceivers, we wanted to see what happens if we bring it up to 120 degrees. And I had to cover this with aluminum foil. Why? Because the Flexbox, this Flexbox has a battery, so it can be dangerous. We have to properly protect it. So I opened one of these, put aluminum foil on it so it's properly isolated, and use the heat gun to get this transceiver hot. And especially for you to find out what are the consequences if this transceiver comes too hot. Will it be damaged forever? Will it recover? What will happen? And I did it in different phases because, I mean, it's important to be careful. And as you can see, I did a warm-up without a heat gun. Can you see the cursor? I think you cannot see it. Well, it's the first phase. I called it warm-up, and I left the program running up to 65 centigrade degrees. And after that, I removed that limit and went up to 100 degrees and was looking what would happen. Would it damage? Would it run into a loss of signal? And yeah, it happened. So what you usually have through your DDM, if you observe your switch status properties, you can see a setting of high warning and high alarm. So I draw this into the diagram, and these are the values you never should hit. So we are going beyond this. And as you can see, we still have signal. So up to 90 something, 80 degrees, we still have signal. We brought it up to 100, which is around here, but there was no signal anymore. So you have a very small margin between high alarm and when the signal gets lost. So you still can drive this transceiver, but I mean, as you can see with the bit error rate, it gets worse and worse. And after that, I tried a cool down. We went up to 120 degrees. What happened? Same effect, but I wanted to see after 120 degrees, does this transceiver recover? And I was pretty surprised. I left it for a couple of minutes and turned it on again. It started with a temperature of 70 something, as you can see here. As DSP and the laser was running, it got a little bit hotter again. It hits the high warning, but then itself it cooled down and it recovered basically. So I have this transceiver here. It's the same transceiver. I heat it up to 120 degrees and it still works. It's pretty surprising. So just as a side information, don't do it. I mean, we don't want to do it. We want to keep our device as cool as possible. But just as a side note, these transceivers are quite stable. Now, this curve explains a little bit what happens if you leave a transceiver running for a longer time. So after 4 minutes, it stabilizes with its bit error rate. And then I left it running up to 1 hour. And as you can see, it jumps between 1.4 and 1.6 times 10 to minus 11. So that is that. You have some stable values. You can trust that after 2 hours, 3 hours, it will not change that much. That is another interesting diagram. What I tried here was to remove cooling devices. Basically, I just turned off the fan and I put it back later on after the temperature went up. And here I have a question for you. This blue curve you see, the bit error rate goes up. It goes up to a value. It gets worse. I have not talked about OSNR yet. We'll get into this, but have a look at the blue curve. Then I put the cooler back, and I would expect, since there's a correlation between temperature and bit error rate, it would go down to the initial value, which is around here, where I removed the cooler, but it doesn't recover. It's like 10 times worse. And now my question to you, why do you think this happens? Where does this effect come from? Any ideas? Retention? What kind of retention?
Your device still contains a lot of heat. It's still 60 degrees. You haven't cooled it down to 30. That's started.
The temperature is here. The temperature is here. It's the temperature was higher before the bit error rate went up, and now it's even cooler. It's even lower. The temperature is even lower after I put back the cooling device. But you are close. It has to do with retention. Yeah?
But you're measuring
Yeah.
You're measuring on one side of the device, so the heat is also on the other side, and it doesn't cool as fast as the side with the cooler.
The retention has to do with the data. Because we are counting the bits, we are counting the errors. That is what the transceiver does. And the thing is, it's a historical value. What you would have to do here is to reset the counter. That's the reason. So you have a bit error rate that is worse, but it's not a big deal because it improved. But you see a worse value because you are dragging the past. It's a rolling average, you could say. That's the reason. But well, that was the boring stuff. I hope I didn't bore you too much. I have something more exciting, and I brought some setup with you. Let me start this demo, because transceivers are a little bit slow. I mean, it's amazing how small they are, but compared to a computer, obviously, or to a Mac, you know, it is a little bit slow. But I want to show you something practical, because our plan is to release an application where you can measure this yourself. We care about bits, how reliable is the connection, so we want to provide this. And what I'm going to do is connect this guy. We have to wait a little bit. And I should put it, here we go. Let me peek to this. Okay, that was not good. Yeah, here we go. Yep, I know. So what are we going to observe here? Well, I didn't talk that much about OSNR, and you might have seen this rectangular graphs on the previous slide. Why are these? Well, you read out from these registers a couple of values, and one of these is the optical signal-to-noise ratio, and basically what you have is a certain resolution. So if you have a value between like 23 and 24, but the transceiver really wants to communicate 23.5, it has a problem. The margin is like 0.25, something like that, but the thing is, if it tries to communicate this value, it has to decide. It's very discrete. That's why you get squared functions, basically. And especially in the beginning, you see some jumps. But as you can see, this is happening currently. This transceiver started with 23 degrees. When it started measuring, it had to boot up a little bit. Now the temperature is going up, and you can see also some oscillating bit error rate, but it stabilizes after a couple of minutes. We can let it run like 1 minute, I'd suggest, so a little bit of curve discussion, but that is what I mentioned. You have like jumps here in between 23.475 and 23.300. It goes up, it goes down again, but after a couple of times it stabilizes. And these are pretty common values, so it doesn't matter what transceiver you take, it is a value between 20 and 30 dB you have an OSNR you should measure. If it's more, that is strange, should not happen, and if it less, you have more noise and signal. That is also bad, right? So no matter what bit error rate you get, you have these values in this section. If it's out of that, you usually don't have a signal anymore. So yeah, that's that. Thank you very much. This would have been... we are not finished yet.
Oh, sorry.
Just 2 slides. Sorry. Was a misunderstanding. We are almost finished.
Get off stage.
So just some small takeaways for you. So bit error rate on direct detection transceivers. This was the first transceiver with a 40 kilometer specification I showed you. Depends on both temperature and fiber length. You saw these strange curves. Then you saw like constant curves. That's the case with Korean transceivers. Bit error rate is a rolling value, as you saw with other curve. Why didn't it get better? Why 10 times worse? You have to look what you are measuring, very important. And with the temperature, yeah, you can go beyond high alarm, but you have a margin like 10 degrees, and after that, signal is lost, right? Thomas?
Yeah. So, and looking at the coherent transceivers, actually, when we look at last year's presentation, there's more than just the property of light, like amplitude, what we use for direct detection transceivers. We have also phase, for example. And these properties make it more, let's say, the signal more ruggedized. And looking at this, the coherent ones, they mainly focus on the fiber length and not that much on the temperature changes. I don't want to say overheat them, but the changes are not so critical just because of the matter we use more properties of the light, and the DSP inside has the capability to recover the signal properly. And finally, now looking at the bit error rate values, what we showed is this is more for the networking people, looking at the BER values. For sure, you can look at OSNR on your link as well. The DSP provides this data, but typically when your BER is within the range, within the specification, you don't have to take care much about OSNR, especially for typical gray optics direct detection ones. Yeah, so that's it from our side. It's pretty awesome that what this DSP can do. There are way more functions inside. Not everything is done in software and firmware yet. There will be improvements in the next couple of weeks and months and years on the firmware side, especially for the transceivers, and that's definitely very challenging and interesting also to look into that. Thank you very much. Now it's Alan. Oh,
I'm gone. Question.
Right. We have time for questions if anybody has any questions here. Could you please?
Well done from Nordic now. So, what about humidity? Does it have any impact?
Humidity. Thank you for the question. We didn't do any tests on humidity, to be honest, because we assume within your data center you control humidity properly. But it's an interesting one to see how we maybe, especially when we increase it. I assume the higher we get, we might run into trouble. Yeah, that's a good one. Okay. You can give it a try with some humidity devices. Thank you.
Okay.
May I add? Oh, okay.
Yeah, so next year you're going to submerge a piece of optics underwater?
Yeah.
Sounds interesting.
100% humidity.
That was a good inspiration.
That's excellent. So if there's no more questions, I would thank you very much for coming here. And you get a piece of chocolate each here.
Oh, pretty nice.
So let's give them a big applause.
Thank you very much.
Thank you very much.